Welcome back to Chemistry for GCC. Now that we have a good understanding of the chemistry essentials that we learned in Topic 1, we move on to Topic 2, which is talking about the atomic structure, composition, and the mole. So it's fitting that we start here because everything in chemistry comes down to the atom. The atom is the basic building block of everything that we do in chemistry. And so Topic 2 is going to be talking about how the atom is composed and how that relates to other concepts such as the mole. In section 1, which is what this video will cover, we're going to talk briefly about the history of the atom. And so recall that we talked about in topic 1, atoms are the smallest quantities of matter that still retain the properties of that matter. An example that we talked about in topic 1 was, take for example a gold bar. This gold bar is only made up of one type of atom, and that would be gold atoms. Now this gold bar has a particular set of properties. It has a melting point, it has a boiling point, it has a density, etc. And the idea is, if you were to cut that bar in half, and then cut it in half again, and continue to do that all the way down to where you had one individual gold atom, that gold atom would still have the exact same properties of the gold bar of atom. So whether it's a bunch of collective atoms together or just one, as long as they're the same element, they all retain the same properties. Now, when you cut that atom in half, that's where the properties deviate, and we'll talk about that in this topic. Now, a little history. You don't need to know all the specifics, but it is good to know the names and general contributions of certain individuals. The idea of the atom was first proposed by a man named Democritus roughly around the 5th century BC. It was Democritus that came up with the idea that everything we see in our world was made up of these tiny things. Now, he didn't actually call them atoms. They wouldn't be called atoms until much later. But Democritus was the first to develop the idea of the atom. Now, he was on a right track. Unfortunately for us, Aristotle, who was, I guess, brilliant, kind of disagreed with Democritus, and he actually believed that everything was made of earth, fire, wind, and water. You may have heard of that Element clothing brand. Great clothing brand, terrible idea scientifically, but unfortunately it derailed Democritus's idea. It derailed what we would call atomic theory. It would not be until much later, around the 19th century, that a scientist named John Dalton would come on the scene and actually revisit the idea that Democritus had so much earlier on in human history. And so John Dalton was the first man to actually formalize the idea of the atom. So Democritus came up with the idea, but John Dalton formalized it in what's known as Dalton's atomic theory, which we'll actually see on the next slide. It's for this reason, and many others, that John Dalton was known as the father of atomic theory, because he was really the one that got us back on the right track, which ultimately led to a lot of the advancements we discovered in the late 19th, but especially 20th century. Just a little information, the word atom actually comes from the Greek word atomos, which means uncuttable. The idea that that was the smallest building block of matter. And so, what was John Dalton's atomic theory? Well, John Dalton's atomic theory is made up of these 5 postulates, and they are, number 1, all matter is made up of atoms. I would never trust an atom. They make up everything. Just because I'm doing videos doesn't mean I can't be funny. So that's the first one. Secondly, atoms are indivisible. You cannot divide them. It's as small as they go. Number 3, atoms of the same element are going to be identical. So if I were to take, for example, a carbon atom and compare it to another carbon atom, they should look exactly the same. Number 4, atoms of one element are different than atoms of another element. So for example, if I looked at a carbon atom versus an oxygen atom, there would be differences. And then finally, it's these atoms that come together to form what we know as compounds. Now, as you read those, some of those you may have been saying, well, wait, I don't think that's necessarily true. I heard differently. And you're right, there are a few of them that we'll talk about in this topic that actually aren't true, such as atoms are indivisible. We have discovered that that's not true. And atoms of the same element are identical. We have discovered that that's not entirely true. But even though there were mistakes or errors in this, and that some of them were later disproven, this atomic theory was huge. It was revolutionary, and it got us back on the right track. And that's actually a lesson in life, right? Sometimes we're afraid to make mistakes, but it's okay to make mistakes. John Dalton made a mistake, but his work, even though it was filled with mistakes that were later on disproven, it still got us pushing in the right direction. And if you think about it, all of the advancements we've made have really happened in the last 150 years because of advancements like Dalton's atomic theory. So we'll revisit the atomic theory later on as far as which postulates are not entirely true. But nevertheless, this got us on the right path. Now, John Dalton also, because of this work, also led to some other things. For example, the law of definite proportions. So now that we had an idea of what we were talking about with regards to atoms make compounds, we were able to start making discoveries such as this, the law of definite proportions. And it states that different samples of a pure chemical compound will always contain the same proportion of elements by mass. So let's break that down, okay? If we think about water, right? Water has the chemical formula H2O, meaning that there are 2 hydrogens for every 1 oxygen. And that'll always be true. But additionally, we have discovered that water is 12% hydrogen and 88% oxygen. Now, obviously, these percentages are not based on quantity. Instead, they're based on mass, because oxygen is a heavier element than hydrogen. But that being said, the law of definite proportions says this. As long as you're dealing with pure water, whether it's a bottle of water, a glass of water, a pool of water, as long as it's water, these ratios and these percentages will always remain the same. So, for example, if I had 100 grams of pure water, I could confidently say that 12 grams of it is hydrogen and 88 grams of it is oxygen because of the percentages. What if I had 1,000 grams of water? Same thing, I'd apply the percentages. I could know that 120 grams of it then is hydrogen and 880 grams of it is oxygen. So that's pretty powerful, and we'll see that later in the course. The other thing is the law of multiple proportions, which sounds the same as law of definite proportions. But there is a difference. And here's what law of multiple proportions states. When 2 elements react to form more than one compound, then a fixed mass of one element will react with masses of the other element in a ratio of small whole numbers. That probably made absolutely no sense. And to be honest, it is kind of a funky definition. I find the best way to explain this is with an example. So let's start from the beginning. When 2 elements form more than one compound. So let's stop right there. Carbon and oxygen are 2 common elements, and when you react them together, they can actually create several different compounds. 3 of those are listed. They could create carbon monoxide, carbon dioxide, or carbon trioxide. Those are just 3 examples of compounds, different compounds, that can be created. So now, with that being said, let's continue on. If we fix the mass of the first element, right, we basically say, okay, let's assume that we had the same mass of the first element. So in each of these 3 compounds, let's say we had 1 gram of carbon in each of those compounds. That's our fixed mass. Then according to the law of multiple proportions, the second element's mass should be in ratios of small whole numbers. And let's look at what that would look like. In carbon monoxide, if you had 1 gram of carbon, that would mean you'd have 1.33 grams of oxygen. The math that we use to figure out the 1.33 is not important right now, but that is true. Okay, so if that's true for carbon monoxide, what if you had CO2? If you had the 1 gram of carbon still, how many grams of oxygen should there be? Notice 2.66. In other words, double what you would have had in the first example. So then, based on that, can you guess how many grams of oxygen there would be in this third example, provided that we still have 1 gram of carbon? And the answer is it would be 3.99 grams. It would be 3 times what you had before. That's what the law of multiple proportions states. So once again, as long as you fix the mass of the first element, the masses of the second element attached should be multiples of small whole numbers. So that wraps up a brief history of the atom. We'll see you in section 2.